So in our last video, we talked about the idea of chemical packages. We talked about ways that we do notation when we're writing molecules. And now what we're going to do is we're just going to get a little bit more practice with the idea of balancing equations that I introduced in my last video. So our first reaction involves the combination of sulfur with oxygen gas to form sulfur trioxide. Now, as you can see, here we have two reactants and we have one product. So we're going to keep all of our reactants on this side and we're going to keep our products on that side. And as you can see, what we're starting off with is we're starting off with a much bigger molecule than we did in our hydrogen and oxygen forming water reaction. We have something that has 8 atoms in one package. So there's your 8 sulfur atoms, and then we have our oxygen, and you can see here that these are much smaller than the sulfur molecules because they have only 2. What we're going to make is a package that has 1 sulfur and 3 oxygens. So let's do that. Here's a sulfur, and we need 3 oxygens. Oh shoot, we only have 2. So we're going to need, obviously, another package of oxygen at the start to get our 3rd oxygen in our SO3 package. Now, if you look at what's going on here, you know we can't be done because we still have 7 sulfur atoms and we still have 1 unused oxygen atom. We need to use up all of our reactants or ingredients for this to be balanced. So we're going to have to make, if you think about it, we have 7 sulfurs left. We need to make enough sulfur trioxides to use up all of the sulfurs. Well, it's 1 sulfur per sulfur trioxide, so we're going to need 1 package for each one. Now you can see we aren't done yet because we can put this oxygen over here, but we still need 3 oxygens in every single one of these sulfur trioxides. So what I'm going to do, I'm going to actually put 3 oxygens in with each sulfur to make sulfur trioxides, and let's see how many oxygens we needed to start with in order to get this many sulfur trioxides. So what we can do then is we can take our oxygens and move these back to the reactant side, and basically for every 2 that I move over, I'm going to say that's 1 molecule of oxygen that we started with in the first place. So you can see we needed a lot more oxygen. And now let's double check that everything is the way that it's supposed to be. I'm just going to move all of this back to the reactant side. And we still only have 1 molecule of sulfur, so we don't need to add anything here, but we now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oxygen molecules, and we're going to make 1, 2, 3, 4, 5, 6, 7, 8 sulfur trioxide. So let's just move all this stuff over to double check that our reaction is balanced. So here's 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. So we have used up all of our reactants and we have made complete molecules on the product side of the reaction. So here's our balanced equation at the top. 1 sulfur 8 molecule, 12 molecules of oxygen gas. Combine, that's what this arrow means, they combine to form 8 molecules of SO3. So as you can see, that was an awful lot of glass beads that we were shuffling around there. And you might be wondering, Robin, do you carry glass beads with you everywhere you go? The answer is no, because we have other ways that we can do it. So specifically, we can balance the same reaction by just using element symbols. And so here's what we're going to do. I'm just going to write out the reaction again. S8 plus O2 gives us SO3. And what we're going to do is we're going to use tally marks to keep track of our sulfur and our oxygen atoms, because right now we are only working with 2 different elements, sulfur and oxygen. In our reactants and in our products. So what we're going to do here is we're just going to look at the way things are written, and we're going to just count up how many atoms of each element there are the way it is currently written. So right now we have 8 atoms of sulfur on this side. 1, 2, 3, 4, 5, 6, 7, 8. And we have 1 atom of sulfur on this side. We have 2 atoms of oxygen on this side, and we have 3 on that side. Now, a reaction is balanced when you have just as many sulfur atoms on this side as you have on that side. So we have 8 atoms of sulfur on this side, and we have 1 on this side. We need more. How do we get more? We get more by adding more molecules containing sulfur to the product side. Now, you could say, how many total molecules of sulfur trioxide do we have to add? Well, you could see we have 8 over here. We need things that contain 8 sulfurs, so we need 8. So let's look at that, and when we add the tally marks, what I'm going to do it a little differently, because what I'm going to do, instead of just putting them all in a line, I want you to remember that we're adding them as molecules that contain 1 sulfur and 3 oxygens. So you can see that by adding more sulfur to our product side, we're also adding more oxygens. We used to have 2 oxygens on this side and 3 oxygens on that side, and now we have 3, 6, 9, 12, 15, 18, 21, 24. So we need 24 over here. How do we get 24? Well, we need to add molecules to our reactants that contain oxygen. There's only 1 molecule here that contains oxygens, and that's this molecule right here. So how many of those do we have to add? Well, we need to keep adding until we hit 24. And you can do this the long way if you want, but essentially what's going to happen is since each of these contains 2 and you need 24, you're going to need 24 divided by 2, you're going to need 12 oxygen molecules. So 1 S8 molecule plus 12 oxygen gas gives us 8 molecules of sulfur trioxide. And that is exactly what we got when we were using the glass beads to figure out how to balance this equation. So I hope that gives you an idea of how to do this. We're going to do another reaction now that's a little different, and you'll see why in a bit. So we're going to now balance a reaction that you have probably seen many times, and that is the combustion or burning of methane gas. Methane is CH4, and although chemists call it methane, most people call it natural gas. So when you burn something, you're always combining it with oxygen gas. We call that combustion. And when you burn methane, in the presence of oxygen gas, what you get is two different things. You get carbon dioxide and you get water, usually in the form of water vapor. You can see now why this is slightly different than the equations we've been balancing up to this point, in that we have two products instead of just one product, and we have three different elements. We have carbon, hydrogen, and oxygen. So once again, I'm going to draw a line here just to help us keep our products and reactants separate. And again, I'm going to make these packages different colors so that we can keep them straight a little better as we add them to. So let's start, and I'm going to use carbon. I'm going to make that carbon, and I'm going to make the greens hydrogen, and once again I'm going to use oxygen to be light blue. So here's our carbon for our carbon dioxide. We have to get our carbon from our methane, and we need two oxygens to complete our carbon dioxide molecule. Now we need to make water. So we need two hydrogens, and we need an oxygen. We don't have an oxygen over here, so we should have probably started with two oxygens. If we started with two oxygens, then we would have one left over to make the water. Are we done yet? No, we're not done, because we still have some reactants left over. We still have two hydrogens and an oxygen. Well, two hydrogens and an oxygen are just another water. This tells us that our balanced equation is going to be one methane and two oxygens, making one carbon dioxide and two waters. And let's just double check that by moving everything that's over here back to the ingredient side. And you can see here that indeed everything we had over here syncs up with what we have on the reactant side. So now I am going to show you how to do that using tally marks. So what we're doing here, we're doing the same thing. We have three elements: carbon, hydrogen, and oxygen. So let's look at what we have at the start.